So let's put this into context. So Steve Sealer quite rightly stated for us that the way this is uniformly done, and the accepted way this is done within endurance, is by anchoring the blood lactate response and heart rate response, not so much heart rate, but certainly blood lactate response, to the external load. So how does this work and why is this done? Well, this is data taken from my textbook, which is on coaching science, and this is from an athlete I've been working with for a number of years. He was a Paralympic athlete. And so what we can see here we've got his external load. So this is his treadmill speed. We've got his blood lactate response, and you can see here quite clearly what Burnley and colleagues call threshold, which I'm now from the rest of this session going to call lactate turn point, which is this point here. So you can see there's kind of a fairly linear-like response in terms of the blood lactate to exercise intensity or external load, and then this sudden systemic rise in the blood lactate response here. Notice the heart rate response is relatively linear, and to a certain degree this is why traditionally coaches would use heart rate with endurance athletes to prescribe an exercise intensity, because it was easy to anchor the heart rate to the external load. The problem is, and I think we perhaps want to clear this up now and then drive into this as we go further within this class, the problem is that is only one internal characteristic. It doesn't reflect what's going on at a cellular level, which you can see here in the blood lactate response. So the net result is I could have an athlete working at a heart rate, in this case here, of around about 162 beats per minute, but because they are actually going to be in the heavy domain, which we'll get into in a moment, because they're going to be beyond this point here, the heart rate won't remain stable. It won't sit at this 162. And if we go into the severe domain, which, as you'll see in a moment, is actually beyond this point, it doesn't always work as it's the consecutive workloads. Heart rate never remains stable, and it will just drift up to max. So you have to be very careful prescribing particularly on heart rate, because you have to understand the way in which all these biological systems interconnect. So why is the lactate so important to us? This is from George Brooks, and again, if you've watched one of the previous classes on the channel, which is about lactate as a mitochondrial fuel, this will be fairly familiar to you. So this is the blood lactate response. This is a conventional, almost textbook working of what one expects to see during incremental exercise, whereas what you saw in the previous graph is actually what we do see. They're similar, okay? You flick across, you can see the curvilinear relationship there. It's just been idealized here. But what we have to understand is that the relationship between external work and blood lactate is actually a function of what we call the rate of appearance and disappearance of lactate. That is, that muscle cells are producing lactate, and in particular it's the fast twitch fibers which are producers of lactate, and slow twitch fibers act as consumers of lactate. And this is why we talked in previous classes about the notion that lactate is not a waste product. It is fundamentally a devolved form of carbohydrate that can be converted back to carbohydrates through processes such as the Cori cycle in the liver. Because all we have is lactate. If you fundamentally convert it back, what you end up with is pyruvate. It's pyruvate and hydrogen ion. So what we have is this appearance and disappearance. So when the intensity is low and we're predominantly using slow twitch muscle fibers, then they are not prime producers of lactate, and they don't need to, because we're not having to recruit large numbers of muscle fibers to maintain the exercise intensity. So the rate of disappearance and appearance are relatively matched. Not perfectly, but relatively matched. And so you can see the rate of appearance slightly exceeds the rate of disappearance. And so you get this very, very gradual increase. But fundamentally, as exercise intensity is increasing, you're having to recruit more muscle fibers. And here's the rub. If you're recruiting more muscle fibers, you're reducing the available number of muscle cells and muscle fibers where lactate can be consumed. And it's about 50% of the lactate that's being produced that is being consumed in inactive fibers. So as exercise intensity increases, the number of inactive fibers starts to decrease until we get to a point, which is the lactate turn point here, which is the big kick that you saw on the previous graph here at 15 kilometers an hour. where the rate of appearance starts to exceed the rate of disappearance. Why is that happening? It's happening for two reasons. Firstly, one, we've got less and less inactive slow twitch fibers to consume the lactate. And secondly, because the exercise intensity is increasing quite rapidly, and we're running from, say, a slow speed or cycling at a low wattage down here to a much higher wattage up here, we're now progressively increasing the number of fast twitch fibers we need to supplement the slow twitch fibers. Remember, fast twitch fibers produce higher forces. The byproduct of recruiting fast twitch fibers is they are producers of lactate, but not consumers of lactate. So now what you've got is you've got a case of diminishing returns. You're recruiting more the slow twitch fibers, but there are less of them now available to consume lactate. You're now recruiting more fast twitch fibers, which are the producers of lactate, so the rate of appearance exceeds its rate of disappearance. So this point here becomes fundamentally important to us. Even if I knew nothing else in terms of systems physiology, I can differentiate that there is a biological difference in terms of fiber type recruitment between exercise below this point and exercise above this point, which is linked to the rate of appearance and disappearance of that lactate.